this is the last video for chapter 7. We only have 3 more chapters after this, so that's exciting. So in this video, we're going to talk about limiting reactants. We're going to talk about some types of reactions. We'll cover more in chapter 8. All right, so before, if y'all looked at any of those problems, they always said excess of one of the reactants, but now we're going to start getting stuff for every reactant. Okay, so there's going to be one that's going to limit how many we can make. So in this example, we still back to our pizzas. We need a crust, so 5 ounces of tomato sauce, 2 cups of cheese to make 1 pizza. So if I have all of these pieces, 4 crusts, 10 cups of cheese, and 15 ounces of tomato sauce, how many pizzas can I make? So we have to do the ratios, kind of like the mole ratio, but this one's for pizza, for each ingredient to see how many pizzas I can make. So I can make 4 pizzas from the crust, 5 from the cups of cheese, and 3 from the tomato sauce. So what limits the amount I can make is the tomato sauce. So that is my limiting reactant. Okay. And the smallest number is going to be the theoretical yield, because that's how much I can theoretically make. So here's just a better visual. Again, the limiting reactant is the one that gives me the smallest number. It's all used up. And then my theoretical yield is the least amount of product. That's the number of pizzas I can make total. I don't have enough sauce to make 4 or 5 pizzas. I only have enough sauce to make 3 pizzas. Okay, so the limiting reactant, it's also sometimes called the limiting reagent, so don't get stressed out if you see a different term, but that's going to make the least amount of product. It's also going to get used up, all of it, most of the time. Okay, the maximum amount is going to be the theoretical yield. That's the maximum amount I can make, not the maximum number that comes out. Okay, this is going to be the smallest answer, because that's the most I can make is going to be the smallest ingredient. All right, and then there's also actual yield. This is the actual amount that can be made. Okay, this is often done in lab. Okay, so most of the time this would be given to you. So often in lab, you've got a theoretical yield, and then you've got how much you actually make. And that actual yield is generally going to be smaller. If it's not smaller, something's wrong, because you can't make more than the theoretical yield. And it's okay that things come out wrong in lab. It's not a big deal. But like if you have enough batter, let's say, to make cupcakes, or cookies especially, I never make the prescribed amount of cookies in a recipe. Never, ever. And that's because I guess my cookies are too big, or they're not uniform. I don't have one of those little scoops. So I always have a less actual yield than I do a theoretical yield, how much the package says I can make. And percent yield is the actual yield over the theoretical yield times 100. So just make sure you always have that times 100 for percents, because percents are always out of 100. And this is going to appear in a minute again, so you don't have to stress out about writing it down right now. Okay, so here we have a reaction with nitrogen, hydrogen to make ammonia. It says, if a flask contains a mixture of reactants represented in this image to the right, which image below represents the mixture in the flask after the reactants have reacted completely as possible. So what you want to do first is count. So I count 1, 2, 3, 4, 5, 6, 7, 8 H2s and 2 N2s. So then we're going to do our mole ratio of each. I need 3 H2s for R to every 2 NH3. So this is our mole ratio piece. So 2 NH3 to 1 N2. And I get 16/3, which is 5.33. And I get 4. Okay, so here is my theoretical yield. I can only make 4 NH3s. So now in our picture, we're looking for 4 NH3s. This one only has 2. Okay, B and C both have 4, but C is the answer. And that's because I have some left over of my H2. So my H2 is the excess reactant. So I'm going to say excess reactant. H2 limiting reactant is into, what else does it ask? Okay. So the excess will always be left over. Sometimes they're both limiting and you have nothing left over. But in this case, whichever one is the bigger answer, that's going to be your excess reactant. Please remember, reactants are on the left-hand side. So you cannot tell me that NH3 is a limiting reactant because NH3 is a product. Therefore, it is not a reactant, okay? So it's just a review. Limiting reactant or reagent, that's the reactant that's completely consumed and limits the amount of product. The reactant in excess, or the excess reactant, that's the one that occurs in a quantity greater than the one that's required to complete the limiting reactant. The theoretical yield, that's the amount of product that can be made in a chemical reaction. And just remember, that's going to be the smallest answer. The actual yield is the amount of product actually made in a reaction, and that's going to be a lab result. And then that percent yield is going to be actual over theoretical times 100. So generally in a problem, it's going to tell you the actual yield, and you'll have to calculate the theoretical yield before you can find the percent yield. So let's work a couple problems. We've got now, the way to tell that this is a limiting reactant problem is notice they give you 2 starting points. And they want the theoretical yield for ammonia. So this is what we're looking for, grams. And we've got nitrogen monoxide and hydrogen gas. So we're going to solve both to ammonia. So starting with our 86.3 grams of NO, I'm going to get to moles of NO. So remember, we've got grams of NO is 1 mole of NO. And I use my periodic table. And I've got 28.01. 14 plus 16. Nope, 30.01. Okay. Then I do my mole ratio. So I have 2 moles of NO to 2 moles of NH3. And then I've got to do mass of NH3. 1 mole in NH3, 17.04 grams NH3. So we can go ahead and solve that now, but I generally just do them both at one time and then do all the calculations. So I don't have to pick up my calculator so many times. So we're doing the same process, going grams to grams from H2 now to NH3. So I've got 2.02 grams. H2 is 1 mole of H2. 5 moles of H2 is in every 2 moles of NH3. And then this last piece is always going to be the same because you're solving to the same product. So this one is generally easier. Now, I do want you to know in the example that the book's going to show you, they don't go through it quite like this. They solve to moles first, and if you're more comfortable with that, that's fine. But I just find it easier to just go ahead and do the whole thing. So for my top one, I get 49.0 grams. And then for the bottom one, $86.4 grams. Okay, so my theoretical yield is always going to be my smaller one. Okay, which means my limiting reactant is NO, nitrogen monoxide. If they ask me excess reactant, that's hydrogen. Okay, so we're going to go through the whole thing. There we got 49.0 grams. Okay, if you want to do another one, you're more than welcome to try that next one. I want to do another one that's got a theoretical yield and a percent yield. Okay, so this one wants us to do way more. We need to find limiting, which you should do anyway. Find theoretical yield in kilograms, but then also find the percent yield. So notice this one gives me 3 values. But this is the key here. It says is produced. This is my actual yield. And again, remember I told you it's going to generally tell you the actual yield. So it doesn't tell us in this problem what we're solving for, but it does tell us the actual yield is in titanium. We do need to solve it for titanium then for both of our problems. So I've got 28.6 grams, kilograms. Carbon. Don't forget, if it starts with kilograms, you can leave it in kilograms as long as it wants it at the end. Okay, I've got 2 moles of C in my problem to 1 mole of titanium. 1 mole of titanium is 47.88 grams. Okay, do the next one, 88.2 kilograms titanium 4 oxide, that's TiO2. Grams TiO2. Ooh, that's a rough looking too. Okay, so I've got 47.88 plus 32, 79.88 is my molar mass. There's 1 mole of titanium for every 1 mole of titanium 4 oxide. And titanium is 47.88 grams in 1 mole. All right. So the bottom one, I get 52.9 kilograms TI. And the top one, 57.0 kilograms. Remember, our theoretical yield is going to be the bottom one, which means titanium 4 oxide, that's our limiting reactant. And now it wants a percent yield, so it gave me actual yield, 42.8 kilograms. I put that over my theoretical, 52.9 kilograms, times 100 because it's a percent. And I get 80.9% is my yield. So actually, that's pretty good yield. But we want to try to avoid yields of less than 50, but often in lab, especially in Chem 1, yields are pretty low, and that's all right. So 80.9, there that is, and that 52.9. Okay, just make sure you know, so I'm just going to walk through this one. 167 grams iron 2 oxide, 85.8 grams carbon monoxide produces this. So this is my actual. Okay, so we solve both CO and Fe2O3 to just solid Fe. And we do the same process we just did with the last one. If you need help, please reach out to me. So, in summary, limiting reactants, or sometimes called limiting reagents, they get completely used up. They're going to give you the smaller answer. An excess reactant is not completely used up. Okay, it will give you a larger answer. Then that theoretical yield is going to come from the limiting reactant, and it will always be the smaller answer. Please, please, please always use the smaller answer as your choice. Okay, I am going to work 1 in excess. Okay, this one is a little different. There will not be any on the test where you have to calculate how much excess. I will only ask you the excess reactant. Okay, so it says, recall further in the reaction containing that, this is the same one as before, so we had 57.00 from our carbon, and then we had 52.9 from our titanium 4 oxide. Okay, so calculate the mass of the excess reactant, which is carbon, that remains afterwards. So here's my theoretical. From your excess reactant, we start from there. Sorry. From our theoretical yield, we start from there. And we solve backwards to our excess reactant. So 47.88 grams. 1 mole. So we are literally flipping all the problems, except instead of going back to our titanium 4 oxide, we're going back to carbon. So there's 1 mole of titanium for every 2 moles of carbon. 1 mole of carbon is 12.01 grams carbon. So this is calculating how much carbon we need to make that much titanium. And I get 26.5. And that's kilograms of carbon. So this is how much is used. Okay, to solve how much remains, I need to take my original amount of carbon, so 28.6, and I need to subtract my used amount, and I get 2.1 kilograms excess carbon. Okay, but you have to do a third stoichiometry problem to get how much was used, and then we can do the subtraction. Again, this will not be on the test. It may be an extra credit question in Mastering Chemistry, though. All right, let's just briefly review combustion reactions. We did talk about these when we were balancing reactions at the beginning of this chapter. So just remember, a combustion reaction is always going to have some substance with oxygen. Oxygen will be by itself to form another substance with oxygen. Usually H2O and CO2 are our products. Okay. Energy or heat is also always going to be a product. And normally what we're combusting is a hydrocarbon. So I'm going to just write a generic. This is a skeletal equation. Okay, so we've got that hydrocarbon, which is normally just carbon and hydrogen. Occasionally there's an extra oxygen in there. Always with oxygen gas, because you have to have oxygen present to have fire. And then we do it makes CO2 and water, and then whatever's left is heat. So, wants us to do a combustion of methyl alcohol. It does tell us it's a liquid. Don't forget these are all gases. Yes. All right, so I have 1 carbon, 4 hydrogens in the reactants, and I have 4 now. And I've got 3 oxygens, and currently I have 4. I have no way to make my 3 reactant oxygens into 4 on the product side. So remember, I told you should always try to start with that combustion as a 2 in front, and then you just multiply everything out. So now I have 2 carbons, I have 8 hydrogens. Now I have 4 oxygens. Plus 4 is 8 on the product side. On the reactant side, I have 4. I'm going to need 4 more. So total, I need 6 out of that O2 because I already have 2 accounted for. Let's do another one. Oh, this one has S instead of O. We're not actually going to do that one. There won't be any like that on the test. All of yours will only have carbon, hydrogen, and oxygen. Okay, there are also alkali metal reactions, and we're also going to talk about halogen reactions. So those alkali metal reactions, just remember that they form that +1 cation. They're very reactive. They have a very vigorous reaction. In fact, you can see in the bottom pictures there that the farther you go down on the periodic table in group 1, the more reactive they are, and they'll create fire in water. It's very common. If we have these in lab, we have to store them under oil so they don't react. Okay, it is common, so they'll react with water. They'll also react with halogens. Okay, also remember halogens are also very reactive. They're the most reactive nonmetals. Okay, these reactions are highly exothermic because they're giving off heat, and they can be explosive. Here's our halogen reactions. Again, halogens can react with metals. They will react with our group 1 metals, but they'll also react with other metals. They are the most reactive nonmetals, and they'll form these hydrogen halides if they're allowed to. So these want you to write a balanced reaction. I'm not going to ask you to do that yet. That's really going to be a chapter 8 kind of thing, but you can just see what they're doing here. Okay. Really, you're just going to need to be able to recognize, maybe in a multiple choice question, which one of these would be a halogen reaction. So if I asked that, it would be halogens, halogens. Or what would be an alkali metal reaction? And then you'd be looking for the alkali metal in there. And that's it. Y'all have a great day.